Okay. So last week we were talking about, this week we're going to be on a short week, as you know, so there's no class on Thursday, but just our Wednesday, just to mention that. Last week what we were doing is, what we were discussing is the inductive definitions or inductively defined types. Inductively defined types, and in fact we came at the end, I was showing the sort of general form, which is the type of well-founded trees. And that's the way to think about it, with a node labeling given by A and the branching factor for each node given by B, and then forming the Brouwer ordinals, these well-founded trees for each of these. And the elimination form for them is essentially some version of what you would call transfinite induction, which is the obvious thing that says inductively you can show that something holds for every one of these trees if for any node you want, if the assumption that the property holds for all of the predecessors, then it holds for the soup, then it holds for every tree. So that's what the elimination form was saying, and that was transfinite induction. And we discussed that this could be characterized as a homotopy initial, so-called homotopy initial. It's when you're in type theory and you're just doing equality, in the presence of univalence, then it's just initial because they're just equal, but the meaning of equal has the flavor of having paths or evidence. So it characterizes homotopy initial algebras for polynomial functors. And I put a post on Piazza because I had a little brain cloud when I mentioned that the last time. So so you can see the Piazza for a brief summary, and it's also, of course, in the hot book for a discussion of that. So I didn't want to make a long story about it, but I kind of wanted to bring out, the structure of inductive types and how they're viewed in this setting, and in particular, this initiality it motivates the conditions on the universal conditions of an inductively defined type, and that their universality is characterized only up to propositional equality. So that was the main thing I wanted to get across. So the point about homotopy initial algebras is that this is the universal property is propositional. Let me just write it like that. That is, that there's the equation that makes things unique is given by a proposition. It's not some kind of definitional equivalence. Okay, so that was what we talked about. So based on given what we're going to do today, these will turn out to be called pejoratively the lower inductive types, because I'm now going to introduce something else which are called higher inductive types. And of course, higher is better, right? So it must be an improvement in some way on what we did before. So that's the idea. Okay, so we're going to do higher inductive types. So the way to think about this, the way I like to think about it is there's two ways to think about it, which is kind of nice. One is, well, there are probably many actually now that I think about it, but the idea is it's some kind of free structure, and the idea is you can think of it, one way to think about it is inductive definition with equational laws. And an example of this would be that you've kind of seen before. It is the idea of like generators and relations, which you probably have seen as a means, and they're called, at least the way I learned the terminology, they were called generators and relations. These are really equations where you want to present free structures, like you want to make the free group on some number of generators. So these are the sort of the generating elements of the group that are going on here. And these are some particular equations that you want to hold amongst the elements of the group. Maybe you want to say something about that it's commutative or something. So you put some law like that in there, or things of this nature. So you can think of it as a generalization of that. So that the idea is that you have the notion of the generators, you have a way of telling me what are the elements, so it's like an inductive definition. But in addition, I have a way of telling you what are some equations or relations that must hold amongst them. But in the setting of homotopy type theory, this will turn out to be a set level concept that is it will live in the notion of zero types. So this is sort of a set level concept that will carry over, but the higher inductive types are actually more general than that. And they're more general because you have all this infinite dimensional structure available to you when specifying a type by what is called a higher inductive definition. Now the key thing that is kind of neat about it is that, so there are two things that are kind of cool about it relevant to homotopy type theory. One is that you have sort of full higher dimensional algebra, if you would like to say that, or full higher dimensional structure. So you could talk about higher groups, which would be, groups are usually, the carrier is a set. That's the usual definition. You have a set and a multiplication, et cetera. And here you could say it's a type. But if you're going to say it's a type, it means it has the structure of an infinity groupoid, which would mean that, for example, the multiplication has to be a morphism of such things. So it has to preserve the infinity groupoid structure. So we have the whole idea of the higher dimensional structure, that is the path structure, at all dimensions available to us, which means that when we impose relations, we can impose relations at multiple levels, as we say, dimensions, or type levels. So it's not merely just elements of a set and relations amongst them, but we could even have relations amongst those relations. Well, how would that come about? Because we have to remind ourselves that in a proof-relevant environment, means that really what we have is generators and more generators. That's the way I would like to think about it, because in the usual setup, there's some distinction between propositions like equations like this, and this is sort of the data and these are the facts about them, okay? And that's like traditional thing. That's I made the analogy before to imperative programming. The data is over there and the program diddles the data. So in a logic point of view, traditional like first order logic, you have some carriers and some algebraic structure on them, some operations, and then over here we have relations that speak about them. So in the proof relevant environment, there's no such separation. That is, everything is just a matter of having generators and more generators. And what do we mean by that? Well, these generators would correspond to, for example, zero cells. That is or we could call these the points or the elements or whatever term you would like to use, okay, of the type. And these are going to correspond to paths. And I'll even emphasize, I'll say higher paths. Okay, because what you're going to do is the way we're going to specify an inductive so-called higher inductive definition is by specifying generators for the elements, the points, whatever word you'd like to use here, the zero cells, and these are the higher paths, so these would be the n cells for higher n, but actually altogether that's really just you specifying n cells, okay? And then informally, what you're doing is you want to look at the free infinity groupoid on the structure that you specify. That's the intuition about what is going on. So in the same way that I was saying, the intuition about lower inductive definition is you look at the initial algebra associated with a functor. That's going to give you that's what we'll consider to be what we're specifying. There's going to be a similar thing, except that the theory of all this, to my knowledge, has not been fully worked out. So there's a little bit of a seat of the pants flavor to this at the moment, at least at my level of understanding. I think that's true. So I will explain how this goes by a bunch of examples. Okay, so that's the plan. So talk about higher inductive definitions. And really, if you now look, the nice thing is that the way I like to think about it is currently, at least, who knows what we might come up with in the future, you could more or less say HOT is by definition ITT, which we started out with the univalence axiom, which tells us that certain paths exist in a universe, that paths in a universe are given by equivalences. So that's a way of identifying types up to homotopy equivalence. So that can be, like, as a matter of mathematical efficiency, it's sort of convenient to do that. And then we add in sort of higher inductive types. Okay, so this I think of as, it's just my way of describing it, but I think of this as a matter of mathematical efficiency. In other words, we know in some sense you can always talk around this kind of thing, but if you're doing, people will say, oh, by convention we don't distinguish between things that are homotopy equivalent, and that's kind of fine on paper, but if you want to mechanize things, well, then there's no chance of having informal conventions. You have to make them formal. And then it becomes really terrible. So in some sense, the univalence axiom, from the way I see it, provides a kind of mathematical efficiency. It makes it come true that equivalent spaces are going to be regarded as equal. They really are equal. And so that's kind of nice. And then this is I think of this as expressive power in some way, expressiveness. Okay, now you can't really draw a distinction. I mean, univalence is an expressiveness thing because it's a comprehension principle for paths in the universe. So it's, in a sense, it's no different from a higher inductive type. It's different, but it's not different. You're just specifying more paths, and so are these. But okay, so in the end, I can't really make this argument, but I'm trying to give you a feeling that my view is that the univalence is a matter of efficiency, and the higher inductives are a matter of expressiveness. What types can I write down? So the idea is that we're now using this kind of architecture that I'm going to describe. We're able to write down types that, well, setting aside univalence, we were never able to write down before, even thought to write down before, as far as I know, in ITT. And so that was the story that I mentioned to you before, is that the funny thing about ITT is that as a matter of empirical fact, it was restricted to sets, even though we now know it was capable of expressing much richer collection of spaces than we knew. Okay, so it was kind of funny that empirically it was all talking about sets in a rather awkward way. So what we're doing now is we're making the awkwardness of ITT a virtue by positively exploiting it. Okay, that's what's happening, because what was previously seen as a vice is sort of renominated as a virtue. That's a way of what is being said here. And then these two things, but in particular hits, are exploiting it. So we had an example of this before, where we talked about the interval, which might be written like this, I, as a higher inductive definition. And the way these higher inductive definition goes, we have an informal way of writing down writing these things down that looks like inductive definitions. So we ended up saying, let's write it like this. So we have 0 is in I and 1 is in I. So these are our 0 cells. We could have called them anything we wanted, of course, but it's kind of conventional to call them 0 and 1. And then in this case, we have 1 cell, where we say, well, in addition, there was something called seg, which is in the identity type for I between 0 and 1. And this is our 1 cell. And then we draw a line around this. We say, okay, that constitutes the definition of the interval. Now, when I gave it to you before, I gave it to you as a primitive set of rules. I just made up some new rules, but it's now going to be seen as an example of a higher inductive definition. So all I'm doing on this board is just to sort of review what we did before, but viewing it as a higher inductive definition. So our point is that, well, modulo, whatever your notation is for these brackets and stuff, you're saying it's given by all and only this data, or the free structure on this data. And the thing you have to watch out for, which is where all of the action is in higher inductive types, is that when you're only dealing with lower inductive definitions, you don't have any 1 cells or 2 cells or anything like that. You have only 0 cells. And then there's a kind of seat of the pants intuition that applies, which is that, well, these are the only elements of that type. So if I omitted this, the way I would inductively specify 2, right, is I would just say 0 is in 2 and 1 is in 2, and then I would say that's the end of it. Okay, so you can compare it to that. And then you get the idea that there's nothing else in there. There's 0 and 1 is the least type containing 0 and 1, so that's 2. And there's nothing to think about very hard in that kind of situation. What happens here is that because we're looking at the free infinity groupoid, see if you're looking at some free set on these generators, there's nothing going on with sets. So as soon as I put those in, when I say free set, well, the whole idea of a set is that it's bare, that there is no additional structure. It's kind of, things are desiccated down to there being mere elements. So it's not too hard to figure out what the inductive definition means. But here, we're always thinking of types, we're inductively specifying an infinity groupoid. And it turns out, and that's the whole subtlety of the subject, which will come up a little bit later, we'll explore a little bit of that. Once you introduce some generators like these paths, they automatically have echoes at higher dimensions, and also even at the dimensions you specify. Because it's implied, for example, that there's going to be another path, seg concatenated with seg is going to be around, right? That's going to be a path in ID, I0, 1 as well, by virtue of the fact that seg is. And other things like, seg inverse will be a path from 1 to 0, and all sorts of multiplications of these, et cetera, et cetera, et cetera, that you could imagine. And of course, reflexivity will be around, let's say you have to say where it's going to be, will be a path in the interval from 0 to 0, let us say, to pick one. There will be another one, and there's other ones, right? So it's all different around. And moreover, as we'll sort of see a little bit later, these are significant, and they induce even higher paths. So the basic intuition about saying, oh, it's these things and no other is not really applicable. That's the main thing to say. Yes?
Seg.seg is not really in there.
Did I make a mistake? Oh, it's not. I should be maybe seg inverse. Yeah, sorry. Because I was thinking of the next example where I get to do that. Yeah, sorry. Yep. Say that again, please. Oh, did I make a mistake again? What?
No, the type should be different.
This goes from 0 to 1 and 1 to 0. Did I do it right?
Well, you still have, you now have 0, 1, so it should change to 0, 0.
Oh, yeah, this would be 0 to 0, yeah. Okay, sorry, yep. Yes, you're right. Yes, that's true. Yep. Okay, I'm actually thinking of what I'm going to write on the next board. That's why I got. Okay, but anyway, I'm just trying to presage. I'm trying to say that there's stuff, there's stuff that is induced by the fact that it's going to be a type. And quite honestly, as we'll see shortly, it's a mystery what is actually induced for many higher inductive definitions. You can easily write down higher inductive definitions for which for certain kinds of questions, people, about the path structure that's induced, nobody knows. They're open problems. Okay, so it's kind of surprising that this very simple idea of inductive generation ends up having it has consequences that no one really understands. Okay, and so that's a very surprising fact. So that's a kind of interesting thing. So the thing I want to say about this is that when I write down, besides the remarks I've made, is that being in this kind of inductive definition, it induces, like, sort of, automatically a recursor. Let's write it up here, and a more generally an induction principle, but let's look at the recursor. So let's do this by the seat of our pants, because the whole story, at least I don't know of a fully worked out story about initial algebras and so on. So I'm going to follow it as if I did know that. Okay. So what I'm going to do is I'm going to think of this as some kind of initial object in a category of things with this structure. Right? So if I think of it like that, then if I have a recursor, it'll say if you give me a type A that has a point 0, a little a, let's say I've written here, and another point B which corresponds to B, right? This is the idea. So what I want to be able to say is you give me this information plus you give me a proof. I want to check my notation. You give me a proof that A is equal to B. Then I should be able to map the interval into it, because the interval is supposed to be the initial thing that satisfies these characteristics. So I say, if you give me this guy, then there's a recursor. I'll call it the recursor on A, given by A, B, and beta. All right. When applied to Z, there's my notation for maps that I'm doing here, which is convenient. will give me an element of A. So this is like saying I have a map from I to A, because it is like saying that this is a map, I have a map from I to A, because A, by virtue of these premises, is a interval algebra, okay, in the sense that this is presenting an interval algebra, and this should be the initial such thing, okay? So that's what I'm doing. And then you would expect, in that case, that if you take the recursor and you run it on 0, well, Genson's inversion principle, on the basis of at least that kind of reasoning, you would expect that to be A, you'd expect this to be B, right? And so that's a sort of what I'll call the beta 0 axioms that I would expect to have these kind of axioms for the 0 cells, which tend to come out definitionally. And then the beta 1, because you see, there's now, one of the, so to say, arguments for the recursor is a path. So there should be a way to extract that path. So I'll leave a little room. So, well, I have to do it like this, which is apply to path. So the notation we've used is if we take the recursor, and I'm deliberately leaving out the last argument, so it's thought of as a function, which is what we wrote as a subscript to app. And but what we're saying is, if you apply it, so one way to think about this is, if you want to put it in, is you can say this is app in the sense of a 0 cell of the recursor, and then shift that up here, make that a subscript and shift that up here. So that's a 0 cell application will give me an A. So this would be a 1 cell application, that's a way of thinking about it, to the same recursor. But now I'm going to apply it on a 1 cell, namely seg, and that should give me, well, then there's the discussion we've had previously. What do I mean by equality? So in some sense, that should be beta, okay? Which is, I'll just write the type over here. It belongs there, but I'll write it over here, which says that A is equal to B, okay? Which I've written down here like that. When I do the induction principle, it'll be slightly more complicated. So in this setting, this is a propositional equality, the way I'm writing this down, at that type. In other words, that's really the subscript that goes on there, but it starts to look bad when I start doing that. So that's what I mean. And so this is what you expect to hold true. And the thing is, as we've discussed before, it doesn't make a lot of sense to even consider whether it's definitionally true, because app is given, it's a defined function. Like I only put those numbers in there just to help you, but app is a defined function that we defined way, way, way back a couple of months ago. And it's not up for grabs to define definitionally what its behavior should be. So that's like a peculiarity. But we can, in fact, demand that it be true propositionally, that app applied to seg, whatever it is, whatever it computes to, will be propositionally equal to beta. And we talked about that before when I gave a lecture on how you would justify the J rule. Okay, so I just want to remind you here. So this tends to hold propositionally, and that's the setup. But intuitively, especially if you use that pseudo notation I was writing down here, on the 0 cells it behaves like that, and on the 1 cells it behaves like that, and we're good. And if you're a little loose about what behaves like means, then it all seems good. Okay, so that's the case. Of course, definitional equivalences are sufficient for propositional equivalences, so those could be written propositionally because they would just be true by virtue of reflexivity. That would be another way of saying it, that reflexivity witnesses the propositional equality of these two things. That's another one thing that one could say. Okay, so that's the sort of, that's the thing. So the point is there has to be some sort of token here. There has to be some witness to this fact. Okay, that's what's going on. Okay, so that's the recursor, and then we can generalize this to the induction principle, which I think is what we did before. So now what we want to do is we want to say we have a predicate. I'll even write A of Z, which is in U. I have a predicate on I. Okay? And now I want to know, I want to end up saying, at the bottom, I want to say, well, for everything Z and I, something or other will prove to me that A of Z holds in general. Okay, so I want to do that inductively. Okay, so how do I go about doing that? Well, what we do here is I noticed in my notes I use a slightly different notation. I said, well, suppose you have A0, which is a proof that A holds of 0. That means plug in 0 for Z. Okay, in here. And if I have B0, A1 I should call it in order to make the notation look good, okay, which is a proof that it holds for A1. And then I have to do something else, okay, which is that I must also supply you what I'm writing here as a path that says that A0, well, okay, this is where we'll have to figure this out, but A0 is equal to A1. It's not really right, as you instantly realize, to say that A0 is equal to A1 because these are different types, you see. A0 is of type A of 0 and A1 is of type A of 1. But this is a family of types, which means that this type is related to this type by a path, namely, right, it's by the transport function associated with the segment. So we can write this as a path over equality. We can write here seg here, and this would be Z dot A. And to remind you, that just means, and then ambiguously, you can do it either way. And we've had the discussion that as soon as I disambiguate this, I make a commitment to the definitional behavior that can be problematic because it introduces subsequent dependencies in a library on it. But we did before decide that we would put it on the left. So that really means transport in the family Z dot A. That's a thing that induces a vibration, okay? And this vibration, the transport, if we transport that along seg and apply that to A0, well, remember, we think of the total space of A, so this was sort of the total space of A, and we have two fibers in question, the fiber over 0, the fiber over 1. We have the segment which links them. So the transport function says, take this guy and send it over here. Okay, it'll be correlated, let's say, to this guy over here. So I transport along seg A0. Now I'm at least in the right fiber. I'm in the fiber over 1. So that will be the image of A0. This will be the image of A. Well, this is where A1 will be. And then we're claiming that there's a path, a vertical path in them. So that's what's being said here, right? So this says this is equal in this case, A of 1 to A1. And as we've previously discussed, I could just as well have said, transport this guy, A1, along the inverse segment and move it over here and then demand that there be a path in that fiber. And morally, there's no difference, but definitionally, they're different. Okay, so that's one of those things. Okay, so we don't know what to do about that. So a lot of times we write it down in this path over notation. A0 is correlated to A1 by the segment. That's the way I like to say it. Okay, so if you do that, then there's a term which is Z dot A, which has all this data. So A0, A1, oops, A1, and P, I've written out here, is a proof of A of 0. Okay, did I do that right? Yep, looks like it. All right, good, we do that. And then we expect, what equations do we expect? Well, we expect these beta 0 equations to hold, which will say, if I take this guy and I run it on 0, that's going to be A0, and that is indeed an A of 0. And if I run it on 1, that'll be A1, and that is indeed an A of 1. And then the beta 1 thing is if I applied a path, the induction principle, which I'll not write out of here again, and I run it on seg, then I should get, and again it'll be a heterogeneous equality, so this will be P, okay, I'll write that this should be true. In other words, in the same way I wrote there has to be a generator here, another way I could say this is that this type has to be true, okay. In other words, there has to be an element of that type, okay? So we'll say that this type has to be true. We talked about that for a while ago. But what exactly type should this be? Well, this would be in the type A0 correlated to A1 over the segment relative to, what did I call it, Z dot A. Okay, so it gets it gets a little heavy. These things start running down the page, but I can't do anything about that really. Okay, so those would be the sort of beta-like axioms that are given to us by a kind of inversion principle. So that's the way we think about these things. And then there's also a unicity. Okay, so there's also a unicity condition, and I will write this as a propositional unicity. And I won't write it out, and the same would hold here. So the propositional unicity, if I really want it to be a universal object in some category of algebras, right, then I need some kind of unicity principle that says, like it's easiest to pronounce out in the recursor, any R that behaves like this on 0 and 1 and behaves like this on seg is equal to the recursor. And therefore, any two such things are equal to each other because they're both equal to the recursor. So that I won't write that out on the board, but you can write down a unicity that says it's a unique such map. And the same would hold here. It's just a little heavier to write it out because of all the path overs things to write that down. So this is what you would expect. So if you view the interval, okay, as a higher inductive definition, okay, then this is the way, then this is what is induced. You sort of have in mind some idea that it's an initial algebra, and you sort of follow your nose. Okay? All right, so that's that. So let's do another example. So there's a little thing, I'll just skip that. There's another example is, and this is the what we usually call the circle, or S1, which will be one of an example of SNs, but we'll start out with the circle S1, and I'm going to discuss this for a while because there's going to be two different ways that I'll be relating. I'll relate two different definitions of the circle to each other because it uses it's exercising the apparatus of higher inductive definitions. Okay, but the main thing to always keep in mind is that what we're doing here is specifying equational theories. We have inductive definitions and then equational theories on them. So we're looking at, in a loose way of speaking, some kind of a quotient of a freely generated structure on some zero cells. Okay, that's the idea. I want to say loosely speaking because the word quotient is tied up with the idea of what is a proposition, what is a relation. So like, I don't want to be too technical there, but informally, the idea is you're imposing equations on this type, and so that's what we do. So we'll be doing a lot of that, and various examples will come up. And there's a lot of discussion in the book about how you can define, I'm going to define a few examples, but there's more that I won't do, that amount to saying, make some structure and then impose some equations. So push-outs are discussed in that context in the book. Co-equalizers are discussed in that book. They're just a diagram and then some equational requirements, and you can just impose them using a higher inductive definition. So the thing that's kind of magic is that, you know, this always works. So the idea about the circle is we say that S1 is a type, okay, and it's supposed to be the circle. So what would that be? So here's one way to do it, which it'll turn out to be I'm going to do two ways of writing it down. So one is that we're going to have a distinguished base point. So this is my zero cell. And then we're going to have a distinguished loop. This is where I got myself I was one step ahead of myself earlier, which goes from base to base. And this is our one cell. And this is going to constitute a higher inductive definition. So when I bracket it like that, I'm just kind of stressing that that's all the information I'm specifying. So I want the free structure on that data. So inevitably, we have to draw that picture. So we'll have, base here is some element of S1. So we're going to have a picture of S1. There's always a reflexivity, the little guy, which never goes anywhere. Okay, and then we're saying that there's another loop. Okay, and the claim is that that's a circle from a homotopy theoretic point of view. because we're not interested in, there's no idea of size or diameter or anything like that involved. So it's just a question that we have a way of making a traversal and coming back to where we started. And the idea is using Fried's notation. This is punctured here. There's no 2-cell there. If I wanted to make the disk, then I would say, moreover, this can be filled in. That's a different issue, okay? But it's a different structure. So I'll just leave that out. But sometimes it's useful to specifically indicate that it's empty, that it's a punctured thing. And so we write it like that. So that's the picture. Now you could reasonably doubt, well, and then I'll give you some partial answer to this, not today. Well, is that really the circle? And the answer to that is, well, yes, because we can prove all of the properties that one would expect of it, okay, to hold homotopy theoretically, will hold of this thing, of this object. So in particular, we'll be able to talk about the fundamental group, which talks about the loops that one can embed in this space, okay, the loops at the base point. And what are the loops at the base point? Well, you can go around and you can go around again. So what I was saying before, which I messed up when I wrote over there, not only do I have loop, but I have loop concatenated with loop is in S1. So that's in the identity type for S1 between, let me write B and B if you don't mind. So for between base and base and et cetera. There's also, like just for fun, I can write loop inverse concatenated with loop inverse. I can do this, all day long. I can write all sorts of things. And you can get a feeling, of course, immediately what's going on here is we can end up saying that if you look at all of these things that you could write down, well, in a sense, to be made precise, those will turn out to be the same as the integers, which is called the winding number, right? So the idea is that these can be calculated out. This is loop squared. So basically, we're going to look at the exponent. So this will be loop squared. This is loop to the -2. And you can write down all of those things. And it turns out there's a 1-to-1 correspondence between that and Z, at least as far as the sets, like basically looking at only the structure of the loops at that dimension 1. Okay, so we'll end up being able to characterize Z. So this will be, the important thing is this will be a set level group, we can say, which means, of course, an ordinary group. But in the context of hot, one could consider higher groups, so maybe it's important to, so that could also be called a 0 group, maybe. Okay, so from conventional notation, that's a crazy thing to write, but it's just a group, but in a larger setting, it makes more sense to emphasize that. Okay, so that will be one way in which we're able to say this really is the circle, okay? Because maybe it's so obvious here because I can draw that picture, but as soon as you get into more complicated structures, I think it becomes somewhat non-obvious that you really are doing the right thing. Okay, so here's the thing. Okay, so that's in any case, whatever it is, that's the definition. Okay, and whatever it may be. Later on, we'll try to argue that it really is behaving the right way to be S1, but whatever it is, it's given by that data. So then we get associated with that a recursor, and now you can see what the pattern is going to be. So for the recursor, I want to say, well, if you give me something in S1, I want to give you something in a fixed A, that's what the recursor is going to do, provided that A, what? Has a loop in it. All right, that's what's saying it, because the class of algebras that we're considering, of which this ought to be the initial one, is types in which there's a base point. What did I call it? Let me try to be somewhat consistent. There's a base point, let's call it A0 in A. So that's playing the role of base, or if you want, I could call it A sub base or something like that. But anyway, let me call it A0. So there's a base point in A, and there's a path in A, which we could call L, okay, which is a path in A from A0, yeah, I did it right, from A0 to itself. And if there is such a thing, then you would think if this is the initial such thing, then there's a way to embed it in there. And the way you embed it in there, and that's what I'll write now, is you have this recursor. So it'll be A0 and L. And you're going to embed it in there in the following way. You're going to say if you take this and L and you run that on the base point of the initial one, then that should be A0, and that of course is in A. So that's in app0, right? And then in app1 says if I apply to path this recursor, and I run that on, what did I call it, loop, then that should be seg. Okay, you would expect, no, that's insane. What am I doing? This should be L, which is in A0 equals A0. This is where we want this to be. Okay, A0 to A0, and I think that that will actually work, right? This will go down here, and yes, so I think that'll be right. Okay, so you would expect that equation. And then again, this is propositional. So what I mean is this type, let's write it down here, A0. What I want is for that type to be true. That's the way I could write that down here. In other words, that should be inhabited. You see, that's where we get the terminological thing about any type is a proposition, any proposition is a type. That's what I'm thinking now. But in other situations, we have used the word proposition in a restricted sense. So that's just the way it goes. Okay, so we have this. And in fact, you could have a unicity. Okay, so eta, which will be the unicity, and I won't write that out again. So if you have an R that behaves like this, then it is the recursor, and therefore, if you have two of them, they're equal to each other. So that's the uniqueness thing. And so that's the recursor. And then we can have the induction, which again looks similar and has very much the same overall structure. So it says if you have a predicate P, I wrote it as P for some reason, on S1, and you have a proof, I called it here B, which is that P holds of the base, right? So we do this. And now the critical thing for the induction is that you want to be able to tell me, okay, that this proof is preserved going around the loop. So that's the way we say it. So we kind of want to say there has to be some evidence. What did I call it just to make sure? I called it L here. Okay, there has to be some evidence that sort of B is equal to B. But that's a little tricky. We have to be careful about what B is equal to B means. This does not mean, okay, that's what's important. Strictly on the basis of type checking, I could write P of base here. Okay, that would type check, okay? But it's not the right thing. Okay, that's the point. It's not the right thing because I don't want to allow, okay, you to have an equation between B and B, a path between B and B, so to say, in the same fiber. Okay, so what I want to be able to do is to say that B is correlated to itself by the transport function of the associated with P with respect to the loop. So this says that it's preserved going around the loop. That's, I think, terminology or something close to that is what's used in the book. Okay? So if we have that condition, then we'll be able to say that for anything in S1, we'll have something in P of Z, and that something is notated the induction principle for Z dot P. And with B and L, I think, is all I need here. Okay, so that's what that is. And everything will look the same, except that, you know, I'll have to put the correlated. This will have to be a path over here, just in exactly the same way that over here I needed to use a path over to express the beta 1 on the segment, so maybe don't make me write it out, okay? So we'll have here beta 0 and beta 1, okay, will hold, and there's a unicity, okay, as well that we'll have to hold there, okay? So that's important. So remember, let's spell out what this is saying, because you can see this quite nicely. It says if I transport with respect to the family Z dot P, which induces a fibration. Okay, so if we have, we transport in the family, if we transport along the loop, because this is fibered over the S1, and S1 has a loop, I want to know that if you transport B, that at least propositionally, what you get back, sorry for squeezing here, you get back B. So that's important. See, you could easily, you see what I mean? Like on the basis of type checking, you could have written the wrong thing here, and then you wouldn't have gotten the right idea, even though it type checked. In previous cases, you basically couldn't have screwed this up because it wouldn't have type checked. Here you could actually make a mistake, okay? And so there it's worth pointing that out. So it says if I transport B from B, if I take B and I run it around the image of the loop in the space that I have here, then I will be able to, I will get B back. Okay, that's the idea. And we know by beta 1, which I didn't really write out here, that if you look at the action, which is, let's look at it here. Imagine that's ind, okay? The action of the loop will be modulo at what type you're talking about, will be L. Okay, so L will be that proof. Okay, so that has to be a proof that it survives a circuit around the loop and comes back to itself. Okay, so that's like a subtle thing. I think it's easy to overlook that. So I wanted to sort of stress that, because if you just follow the pattern, then you'll well, anyway, that's it. So it has the same pattern as what we did for the interval. Yeah.
You said with the higher inductive definitions, you can quickly define a few equations and not be able to reason about the full consequences of those. Do those correspond to properties in homotopy theory? Yeah,
that's why that's what I'm alluding to.
Yeah.
So what's going to happen is, now we have S1. In a couple of minutes, I'll be able to talk about the higher dimensional spheres, and then everyone kind of knows if you look up, that the various questions you could ask about paths at higher dimensions in the various spheres are not well, there are a lot of question marks. Okay, people don't know. Okay, so all I'm saying is there are standard questions one asks about the structure of paths at various dimensions or loops at various dimensions, and for various combinations of even just spheres and which question you're asking, it can either have answers that are you certainly can't eyeball them. Okay, and or they don't have answers at all. Okay, and they often are derived on the basis of it seems to me are derived on the basis of general theorems. So they'll be able to say, okay, some particular spot is filled in by some crazy group, and you say, how do they ever think of that? And I think in most cases it's because it's derived as a consequence of some other characterization of the particular situation. So that's what ends up happening, because they're not. At least to me, they don't look like anything that you say, oh yeah, clearly. Okay, it's like they don't even look anywhere near like anything you could think up. So it's all very nice at S1. S1 is so beautiful, it's great. It sucks you in, okay? So, because there you can kind of eyeball it, you know what's going to happen, okay? So, but other than that, you can't. Okay, so now let's say something else about S1. I have to figure out where I want to put it. I'll put it here, I guess. Okay, so there's some nice things, because what I'm going to do is I'm going to say something about S1, and then I'm going to, about S1, and then I'm going to recharacterize S1 in a different way, and talk about the equivalence of those characterizations, because the recharacterization that I will use is itself useful in other settings. Because you could ask yourself just at this moment, you might be able to follow, you probably could follow your nose if I said to you, okay, everybody take out a piece of paper and write down what S2 might be. You could probably come up with something that's good. You might come up with something that we might have to prove is good. But there's a more systematic way of doing it, so that's what I'm going to get at. But before I get at it, let me do this. So recall we showed, and I put a follow-up post on Piazza the other day about this as well. We recall that I don't know, whenever it was, a couple of weeks ago, we said the nice thing about the interval, okay, is that you can use the interval to characterize the total path space, the total path space of A, which was by definition sigma x and y in A, the identity in A x, y. So the total path space is, well, what it sounds like. It's all the paths that are in A. Pick any two endpoints and then associate with that a path between them, and then the sum of all of those is the total path space. Okay, so we showed that. We talked about that before, and this makes sense because you see a map from I into A must exhibit a path in A because it's got to send 0 to something, A0. It's got to send 1 to something, A1, and it's got to send the segment to a path between them. Okay, so it's picking out a path in the total space. Okay, that's what it's doing. And so that's really nice because this is the sort of type theoretic thing. So this is what we get in HOT. The way we think about paths in HOT, well, at least, you know, the whole starting point of HOT is to think of the identity type in a proof relevant setting, that the proofs of identity, the identifications, are paths, and then we just say, let's work with that as an abstract type. But this is nice because this is sort of the, I don't know, for lack of a better thing, the usual way, except you have to be a little bit careful. It looks like the usual way, because the usual way is, well, usual, at least in top maybe, what you do is the I is the actual interval piece of the real line, and you think of a path as a set of points, and so if you have a continuous mapping from the unit into the real unit, the real unit interval, literally, the real unit interval into A that is continuous, then what you're doing is you're tracing out a set of points in A that goes from, let's say, A0 to A1. So there's a notational game going on here, which is we're doing an abstract version of homotopy theory, so we're not really working in top. We're working in a somewhat more general setting, but we can legitimately read arrow as continuous functions if we want. And so you can see that because nothing in type theory would refute that. In other words, it's a legitimate way to think about it. Then you realize that it's not merely a notational trick. It's the abstract way of saying why that was a good, in retrospect, why was that a good notion of path? Well, because of this equivalence, okay, that we can do. So we did that. So we talked about that before. So it turns out you can do the same sort of thing, which is, so what we'll say here, now that we have S1, there's a similar thing going on, which is a characterization of what is called the loop space of A. Okay? It's written like that. In fact, I want the integral of the loop space of A. And what do I mean by that? The total, this is the space of all the loops in A, which is all the paths from X to X. So by summing them up, what I mean is I'm looking at all the loops. If I pick this is called the base point of the loop. If I pick a particular base point, then I will be talking about the loop space of A at that base point. And sometimes people work with pointed spaces, and so it's implied what the base point is, and then you just say the loop space of A. But so let's be careful. I'll write it like that. So look at for the total loop space of A. That's the way I'll say it. Okay. So we'll write it like that. And how can we characterize that? What would give us the type of all of the loops in A? Well, it would certainly be the mappings. It ought to be the mappings from S1 into A. Because if I put parens in just to be careful, right? So the idea is that, what does it mean to give a mapping from S1 into A? It means you give me a base point in A, because that's the image of base over here. And you give me an image of the loop, which is a one cell. So you're going to give me L, which looks like that. So you're going to be identifying a loop in A by a map from S1 to A. That's what you're going to do. And indeed, we're going to claim that that really is a loop in A, because according to us anyway, that's what a loop really is. I mean, that's the hot perspective. A loop is really this. Of course, in a different setting, in the traditional setting, the usual setting, this is what it really is, and this is some crazy thing that some other computer sciencey people thought up. But this is the sort of, but from our point of view, this is the real thing, and this is what we'll be able to characterize it as. Okay? So you can easily do that. So how do we do that, right? So we want to do that. So we'll go from left to right. So we can define. You can see where this is going. This is pretty clear. So we have S, which goes from S1 to A. I want to define it over here and then exhibit a quasi-inverse, right? Okay, that's what I want to do, right? And what do I do? So we define it by lambda G, let's say here. We do that, call that G, and then what do? I got to inject into that space. So I look at just what I said to you before. So the base point in question is G of base, and the loop in question is the image of the loop under G, under G, which is given as an argument. So F is what's going to turn out to be an equivalence. Okay, so we do that. Okay, so that's the idea. And if you remember what the typing for app is, its type is G of base equals, it's a path from G of base to G of base, okay, inside of A, if you work it out, okay? Because that was the thing that takes paths in the domain, namely loop, to paths into, that's what app does, into paths in A, and the path it takes it to is there. So that it's at least plausible, okay? All right, and so now there are different ways of showing that F is an equivalence. So I want to show that this is an equivalence. And it turns out that the easiest thing to do is to show that for every L in the loop space of A, the total loop space of A, that the fiber of F over L is contractible. Because remember, the fiber over F is the preimage of L by F. So you take a loop in the loop space over here, the total loop space, and you look at all of the S1 arrow A's that map down to it, and you show that that's 1 to 1 and onto. Okay, that's the idea. Remember, we talked about that? So this ends up saying, modulo the definition of equality in hot, this basically says there exists a unique G, okay, such that, well, so because that F maps to L. That's what that is saying, okay? And you can check that. So that should make sense. I won't do, it's a straightforward thing, okay, to prove this, so I won't write it on the board. But what you do is you show that the fibers are contractible. So this is remember we had like 3 reasonable definitions of equivalence, and one of them is a function like this is an equivalence if all of its fibers are contractible. That was one of the definitions, okay? So, so we did that. I did, damn. So I won't repeat that. Okay, so in other words, show that it's 1 to 1 and onto, but the fancy way to say it is the fibers are contractible. Okay, so we say that. Okay, so that's what we do. All right, so good. Okay, so that's a nice, I just think it's kind of nice. It's very elementary, but it's nice, right? So that's part of saying, I mean, it's not the whole story, I guess, but it's part of the reason why we ought to call the thing I'm erasing here, why we ought to call it S1. It wouldn't be S1 if that didn't work, or, you know, or we really shouldn't call it that, let's say, if that didn't work, because otherwise we're misleading you. So it starts to feel right. It was good to call this the interval because, for example, we have that property. It may be one element, one aspect, a necessary condition, let's say, of being S1 is that this equivalence holds. Okay, so I'm going to skip some things. And let me now talk about what is called suspension. Okay, which is, so the question, one way to motivate this is, I'm going to motivate it by saying, here's another definition of S1, and then we want to see that those are equivalent. And this other definition has the characteristic that it can be iterated in a certain way, and it gives us a nice way of talking about what Sn is for any n. Okay, so that's the idea. So the suspension is going to be the thing, okay, that takes us from Sn to Sn plus 1. That's what's going to happen. And it'll turn out to be S1 is the suspension of S0, which we just defined to be 2. And then that will make things work out. And then I think there's a remark in the book that I hadn't thought of before. You can actually think of 2 itself as the suspension of void, of the empty type. And so you could call that S minus 1. So you can start at minus 1 if you like. Okay, that's just like a cute observation. I never thought of it. I was reading the book and I thought, oh yeah, that's true. Okay, so let me explain what suspension is and then we'll see it. So here is the sort of picture. So another picture. So if I had asked you, another picture / definition of S1, if I had just asked you to define in hot S1, maybe you would have come up with this picture. It's just as reasonable as anything else. You might have said, well, we'll have a point here, we'll have a point here, and then we'll have, I'll try to draw them nice and curvy, okay? So we'll have 2 paths here, like that, and we'll call that N and S. Let's call that north and south, because you can see where I'm going to head is S2 is going to look more like a sphere in 3 space, and so there'll be a north pole and a south pole. That's the whole idea. So there's a north pole and a south pole, okay? And we're going to have 2 things which are called the meridians. Oops, I'm sorry. I'll call that meridian of 0 and meridian of 1. Okay, there's a reason to do that. I want to define them as a function of this underlying type 2, okay? So this will turn out to be, I'm going to use a different notation than's in the book because it's a little culture clash. So normally this is called sigma 2, and that's perfectly fine as long as you're not using sigmas all the time for other things. So I'd rather not do that, so I won't do that. It's just unavoidable. So I'll call that susp of 2, and that will look ugly to people who like the other one. But sorry, anyway. So we'll call that susp of 2. That will be called the suspension of 2. There's going to be a pattern here, which is what I want. Okay. So if I wrote that as an inductive definition, and let's just say this is my inductively, I'm going to define it, this. So this will be my S1. So what are the generators? So I wrote this out. What I will say is I have N, which is in S1. This would be the way I would do it if I were doing it by hand. I would say S is in S1. And then I would say the meridian takes 2, N equals S1, S. Maybe I should underline those or something just to like somehow indicate that they're supposed to be sort of like constants that I'm using to generate there. Okay, or I'm capitalizing them. So that would be the inductive definition corresponding to that picture, okay? And, well, it looks circular, right? Okay, so you say that seems like it ought to be a circle, and we will be able to do that, okay? We'll be able to show that that is in fact the equivalent. So in fact, you could do it by hand if you want. It'll turn out to be, we can do something else, but it turns out as you can show like an exercise here, it's kind of nice, as well. I need some definition. So basically show that S1, the first definition, sorry about that, is equivalent to S1 in the second definition. And that will be true, okay? So you can check that. So that's the same as just having a loop. You can kind of feel it, of course, because if I go, let's say here and this backward, that determines a loop at north, right? And you can work from there as what's going to happen. Okay, but now let's look more generally at the notion of suspension. So what we'll do is we'll look at susp of A. And I spent a little while trying to figure out what is the best way to write this. I'll do my best to draw a picture. I hope it appeals to you, okay? So what we do is we define susp of A like this. So we're always going to have a north and a south. These are going to be our 0 cells. Okay, so these are going to be our 0 cells. That's the idea. But now A is, like, we don't know what A is. A is just a type, right? So this is where, this will wind up being in U when A is in U. That'll be, like, the comprehension principle for higher inductives will be like that. So it's going to be a type. That's going to be in U. So it's going to have these 0 cells, okay? And then we're going to have this meridian constructor. But of course, there's not just 2 2. So then the question is, what is it that made this have 2 meridians? That's the tricky part. Okay, so here comes the picture. Okay, and so I will do my best here. But the idea is that, well, let me specify this. What we're going to do is we're going to say that for every, there's an important point about hot is going to emerge with my words here. Let me say it naively, and it'll be not quite right. I could say for every point in A, I'm going to assign a meridian, okay, in susp of A between north and south. So that, let me just put that in there just to emphasize, okay? So that is going to be my definition, but my pronunciation of it, you have to be careful, you have to be very careful, because this is a function in hot, okay? So remember, this means 2 things. As it sends points in A, will be sent over 2 meridians. So if you give me some points, you know, A, then it's going to send it to a meridian, okay? But moreover, it respects the path structure in A. So if you give me, so to say, equal points in A, right, then it ought to tell you that the meridians are equal. A and A prime, yes, are equal. Okay, so you have to remember that, right? In other words, this is a functorial, or loosely speaking, continuous assignment of meridians to the points in A. Okay, so that's the way to do it. So what's happening is, as I said, this is going to be susp of 2, because what's happening is we're defining over here, we have our north and a south, and we'll call those maybe west and east, okay, are the 2 meridians that are going over here. And those are being indexed by 2, okay, that's what's going on here. So this is susp of 2. We can write it like that. I have a reason to write it west and east. By definition, that means meridian of 0 and meridian of 1. I want to write it like that because it helps me draw the next picture. Okay, wish me luck here. So now, what is susp squared of 2? In other words, what is susp of 2? Well, it has a north and a south, because it always does. So that's a different north and a south. So it has a north and a south. And now it has a meridian, right? Assignment of a meridian to each element of A, which is susp of 2. Okay? So now we have to be careful, like, what do I mean exactly here, okay, by susp of 2? So what's happening is there's a meridian here corresponding to each of the 0 cells. That's what I mean about the functoriality. So let me write parens n here. There's a meridian corresponding to north. You see what I mean? And there's a meridian corresponding to south, because those are the 0 cells of susp of 2, right? And then we have the west and the east, which says that there's a functorial dependency. And so the functorial dependency is that the picture is, and now here's where it's going to get tricky. Associated with west, I'm going to have these 2 cells, which I wrote paren W and paren E, which relate the one associated to north and the one associated south to each other. Okay? That's what's going on here. So if I put a little X here just for the heck of it, okay, to indicate the indexing, that this is the edge that's indexed by north, this is the edge that's indexed by south. That's what I mean by of S and of N, because, okay, that's N and S there, okay. And then because of the preservation property required, there's a 2 cell associated with W and E, which I write like that, okay. And now if you just kind of squint a little bit and you kind of move these over here, you know, and kind of make these guys come together, and then sort of forget about the arrows because they are oriented but they're reversible, so we could just forget about the arrows, then it kind of looks like this as a S2. Okay? Of course, that doesn't prove anything, but I'm trying to give you a flavor, okay? So that's the picture that you have. Okay, so good. I think I actually spoke sensibly there. That actually worked. Okay, good. So that's the idea. So that's the way in which we do the assignment. So the claim is, this has to be, the claim is basically this is S1, and this will be S2, which we think of as the sphere in 3 space. If you think of it embedded in 3 space, that's the way to think about it. So this is a globe or a ball, but it's the surface. It's not filled in. It's not like this is hollow, so to speak. All right, and this is hollow as well. Okay, that is, there's nothing relating these two guys, so that's sort of punctured, and so that I don't know what else to do. Puff your cheeks out. Okay, so that's the way that should be thought of. Okay, so if you do that. Okay, so now we get principles of induction and recursion associated with suspension, which we will need in order to establish the equivalences I was mentioning. Okay, so that's the idea of suspension. Okay? All right, so now what do we do here? So we're going to, as usual, think of sus of A as the free sort of suspension algebra, okay, on some, as specified over there. So if I want to get to some B, I'm guaranteed to map into B. It's going to be the initial one. If B itself has sort of suspension-looking structure, so it has a B and an S, N and an S, excuse me, a sort of north and south pole. And there are different ways to write this, but one is for X in A, we have, let's call it M of X, is a proof that north is equal to south in B. Then the recursor, with B as the target, with N and S and X dot M, is the thing that witnesses that you have an element of B. And then you would expect a zero cell thing, which says that the recursor, when applied to north, should be N, clearly. When applied to south, should be S. And then you'll have a beta 1, which says that if you, for every A in A, because this is a parameterized type, okay, then if you do the app of the recursor, okay, to a meridian indexed by A, then that should be, this equation should be true. A for xm should be true. Should be true. In other words, this is again the same issue over again. This is propositional, and we're demanding that equation be true. That's sort of the least we could ask, okay, is for that to be true. Okay, so that's the idea. And then there's also suspension induction, which says, I'll do it in place, which says if we have a Z in sus of A, get a bigger piece of chalk, that B is a type, then what we're going to do is we're going to demand that north be true of, let me check myself, B of N, N be true of B of N. This would be B of S, okay? And then what do we do about the meridians? Well, we have to have a proof, okay, that N is equal to S, but now we have to preserve the meridian I'm looking at the wrong spot here, give me a moment, at the meridian at X, right? Meridian at X. It has to be preserved by the meridian at X. So it's the same argument we did before, and then this will hold for B of Z. I call this ind in that case when it's induction, and it has a similar kind of requirement, except that now this be a path over, because here, in the case of the recursor, that symbol B, that will have to change, okay, when we, that'll have to change when N equals BS. So this is, in the recursor, it's N equals BS. When you do the induction, this will be a path over Okay, that'll change there. So it'll be a propositional equality. And that has to be true. So that's the principle of suspension induction. Okay, and I'm out of time. Okay, so I will pick this up next time, but that'll be a week from today. So what we'll do is we'll characterize all the spheres in terms of S1, and we'll generalize this kind of thing by talking about the higher loop spaces, the iterated loop spaces, and relate them to maps from S1. So you can kind of think that what's so special about loops? We could also talk about the balls or the spheres that are embedded in A, and those will be images of S2, and so on. At some point you don't have any words. The nth iterated loop space will correspond to maps from Sn into A, and the way we'll get that is not by going, well, by characterizing it in terms of suspension. So there's a general theorem about suspension in loops. So basically the suspension of something and be the one more iterated loop over here, and we'll prove that those are equivalent. So this and this, and this is like, I will end up being the disk, so it's a little bit different. It's like S0 or it's like D0 is the way I would think about it. But there's a pattern that relates them. This is sort of the filled in version of it. So you could sort of ask, what happens about the disks that I map into A, and you can do a similar thing. So that's the idea about how that will work. Okay? So the general idea, the reason I went through the trouble of talking about initial algebras and all that was to sort of say, to motivate for you why you would have how these limb forms come about. And it's always just from the idea that it's the initial such thing. And so to get one, you have to exhibit a type or family of types that is closed under the relevant structure, and then you say it's the initial one. So that's how that works. So that's what the recursor is doing. And so that's what I wanted to, that's why I did that as a preliminary discussion, because it helps it motivate what we're doing here. Okay, and so then we'll play around with this, and then my current plan is to finish up with doing the fundamental group of S1 and a proof of that, and that'll probably take us, that'll be basically it. So, okay, all right, thanks very much.